Okay, everyone, we're back in section 4.13, studying least squares for classification. So the basic idea here is we're going to be using some of our regression skills that we found before to treat the classification problem as a regression problem and just learn weights that will best try to match the class labels, treating them as just ordinary numbers rather than, binary labels for the different classes. So let's get into it. Okay, so it says in chapter 3 we considered models that were linear functions of the parameters, and we saw that the minimization of a sum of squares error led to a simple closed form solution for the parameter values. So therefore attempting to see if we can apply the same formulas into classification problems, okay? So consider a general classification problem with k classes, the 1 of k binary coding scheme for the target vector t. So this is just the one-hot approach. Now, one justification for using least squares in such a context is that it approximates the conditional expectation t given x of the target values given the input vector, right? So, and this is coming from the idea that when you're going to report a point estimate given some distribution of your data, the best point estimate you should report depends on the loss, how you're penalizing errors. And if you're penalizing errors according to the least squares loss, then your point estimate should be this posterior expectation, or the expectation given your probability distribution. So in our case, we're going to have some data, and we should then report the expectation of the posterior, to minimize least squares error. So we know that. The least squares in this setting will be trying to do that. And that seems like a reasonable thing. That could be reasonable. So this, for the binary coding scheme, the conditional expectation is given by the vector of posterior class probabilities, right? So that's not a bad thing to want to approximate. Unfortunately, however, these probabilities are typically approximated rather poorly. So, we're going to try to achieve this value. We're not going to actually be able to do it. And the values that we do get aren't going to be, interpretable necessarily as probabilities because they're going to fall outside of the 0-1 range. Okay, and this is due to the limited flexibility of a linear model, as we shall see shortly. Okay, so each class C of k is described by its own linear model, so that y of k of x is wk of t of x plus this offset. So just the main idea here is that we're kind of just going to treat them independently, and so these weights, each class is going to have its own weight and its own offset. Okay, so let's just keep that in mind. We can conveniently group these together using vector notation so that y of x is equal to w transpose. Okay, so let's just so this is going to be equal to right. So this is going to be a vector of y1 to yk, and then inside here is going to be wk. I guess transpose, and then wk o. And then you're going to be multiplying this by this thing that's dependent on how you want to arrange things, but you could put that on the other side as well. And it's going to be x and then 1. So that's going to include, that's just one way of including. So these x tildes are going to include that bias term in them. Okay, so w, and I've highlighted these in kind of light green to help us keep things straight. So W is a matrix whose kth column comprises a d plus one dimensional vector, so and so. Okay, and X is the corresponding augmented input vector 1xt with a dummy input on it. Okay, so let's just highlight the augmented aspect. Okay, all that means is that you can absorb the bias into the weight vector rather than having to deal with it separately. All right. So all we're going to do now is just the natural thing, and we're just going to determine the parameters by minimizing the sum of squares. So we're going to try to essentially, for every single point, we're going to compare what comes out of there and just compare it to that one hot vector that we want, for the corresponding data point. So that's all we're going to do. Now the sum of squares error function. Oh yeah, so let's just make sure we know the way he's setting up the value. So consider a training data set x of n, t of n, where n is equal to 1, 2, capital N, and define a matrix T whose nth row is the one hot vector together with a matrix x tilde whose nth row is the corresponding inputs. The sum of squares error function can then be written as this. And it's actually quite convenient to write things this way. We'll see that I'll just show you if it's not clear, I'll show you that it is doing the right thing. But it's clear because then with just a couple of steps, you arrive at the solution that you need. So now let's just look at make sure this is giving us indeed the answer we want. Well, if we look at let's just look at the first component of this. So this is going to be x1. I'm just going to transpose times w minus t1. And then so that's going to be, we're going to be looking at the 1, 1 column of this giant matrix. And then that's going to be multiplying by itself, right? And so, well, that's just, x1 transpose w minus, and this t1 is a vector, right? It's a one-hot vector. So we're just going to be measuring the difference between, our predictions, or that our corresponding y, and the one-hot binary vector. Okay, so that's going to be, the square difference. And now then this trace just sums all of those up. So it's going to just, this trace then is going to equal to the sum, 1/2 of the sum over n of xn transpose minus tn. And these are all, and this is a matrix, this is a vector. Yeah, you're not missing much. I'm just writing the squares there. Okay, so that's this trace formalism is one way of just writing that expression that we need, the sum of squares over all of the examples. But the cool thing about writing it this way is then it just gives you, in a couple of lines, which we'll just do now together, it will give you the solution. So if we just do that, we'll just write the differential of this. So dE is going to equal to the trace of, I'm just going to drop the tildes, t x dw. So then from that we get that the gradient is going to equal to x transpose xw minus t, and then setting this equal to 0 goes to x transpose xw is equal to x transpose t. So then w is x transpose x minus 1 xt t, which is precisely this expression. Okay, so it's just a very easy way of arriving at the answer, basically. Okay, and let's just try to understand. So hopefully, let's just try to understand what this is doing. So we got the answer. Does it make sense? And the way to look at it is, because we're going to treat each of the columns one at a time, right? Like notice that the same kind of pseudo inverse is being applied independently to each column. So what are the columns, right? So there's going to be, whatever that is, and these columns are like, let's say 1 0 0 0 0, 1 0 0 0 0 1, and so on, right? These are kind of the one-hot labelings, and this is k elements for each of the classes. So we can just look at one of the classes and see what's happening. So and the way I try to understand these expressions like this, I just pretend that, let's say this was just equal to the identity, right? So let's say that element was gone. So what would actually be happening here? Well, you can see that what would we be doing would be the corresponding element, I'm just going to let it write it like that, like the corresponding element of W, let's call it W, we'll just call it W1. So this is going to be a column. Well, what is that going to be? Well, it's going to be the sum. So notice that, so the rows of X are the various samples. So now this is going to be, let's just do that. So it's going to be X transpose, and I'm just going to call that T1, say, okay. And what is this? Well, if we actually expand it out, it's going to, all of the samples are now going to be in the columns of X transpose, so X1, Xn times T1. And we see that this is just going to be the sum of over all of the Xn, T1 of n. So what we're doing is we're actually creating a column vector by summing up all of the samples that have for that class, right? This T1 is just going to, you can actually write this as sum of Xn such that, n belongs to, I1. So we're saying here that the weight is going to just add up all of the columns, all of the samples that are in a particular class. And that kind of intuitively makes sense, right? So if we want to find a vector, weight vector that picks that class out, well, why don't we just take, maybe take the average or the sum? That seems like the right thing to do. And that's basically what's happening here, except as always, you just need to account for the correlations between the elements. So like what if you have, what if there's lots of, the elements for class 1 look a lot like the elements for class 2. So then the best thing to do isn't quite to just add them up. You have to kind of like account for that overlap. And that's what, this kind of decorrelation matrix does for you. But the basic idea is this, of just, you're essentially summing up all of the elements and then adjusting for their overlaps, or you can think of summing up all of the adjusted elements. So you can adjust the samples first, to kind of make them, to kind of separate them out. And then you just do a weighted sum. You just grab all the ones that belong to one class. So this expression, it can, you might be already used to it by now, but that's kind of what it means, and it makes sense. Okay, so let's continue on now. Okay. Right. Okay. Yep. So that's what we got. Good. Where x is a pseudo-inverse as discussed. We then obtain the discriminant function of the form so and so. Okay, so we're again, and these, so now we've got, for example, so y of x is going to equal to w1 transpose x, w2 transpose x, and so on. And then let's see if we can kind of make sense of how this thing works. And again, so what we can actually play kind of the same kind of game, right? So T transpose, well, it's going to be like all of those one-hot vectors for each one of your samples. And now, again, let's pretend this x dagger thing is actually just x transpose. So it says, so what are we doing? Well, now this term here, well, it's just going to be how correlated is our input with each of the samples, right? So let's just call this, we can call this as T1 to Tn, and let's just call that, I'm going to call that R1 to Rn, right? That just is how similar is our new point to each of the samples. And then it says, well, the result you should spit out, it should just be a weighted sum of those one-hot vectors according to those correlations. Right, so it says, and again, that makes kind of intuitive sense, right? It says, if this x tilde looks a lot like an x from the first class, well then, we should have that, that should show up in y. That should show up in the output, and that's exactly what's happening here. But again, you have to account for the overlaps between the samples, and that's where the little complication term here is. But the basic idea is exactly kind of analogous. Here we're adding up the samples. Here we're adding up the labels to get our prediction. Okay, so again, kind of intuitive. You can kind of think of it that way actually yourself when you're like, you could kind of guess these answers just with those concepts of, okay, well, what's the weight vector? Intuitively, how would I pick the weight vector, and how would I pick the outputs? And you'd probably get most of the way there. You might just forget this kind of decorrelation aspect. All right. So let's keep going. Okay, now it says an interesting property of least squares solutions with multiple target variables is that if every target vector in the training set satisfies some linear constraints, then the model predictions for any value will also satisfy those same constraints. Okay, and there's an exercise you can do to show that. So thus, if we use a 1 of k coding scheme for k classes, then the predictions made by the model will have the property that the elements of y of x will sum to 1 for any value of x. Okay, because the targets do. However, this summation constraint alone is not sufficient to allow the model to be interpreted as probabilities because they're not constrained to lie within that interval. Okay, so we've got things summing up to 1, but the actual values themselves aren't going to be probabilities. Because probabilities need to be strictly between 0 and 1, and these won't be. Okay, nevertheless, let's see. Is that the only problem? So it says the least squares approach gives an exact closed form solution for the discriminant function parameters. However, even as a discriminant function, where we use it to make decisions directly and dispense with any probabilistic interpretation, it suffers from some severe problems. Okay, so we've already seen that least square solutions lack robustness to outliers. So remember, they will tend to be really swayed by the points that are way out because of that squared loss, right? They're, the farther out you go, like the effect is kind of going up in the square of that distance. So you're going to be really trying to, account for those points way out there. And this applies equally to the classification application as illustrated in 4.4. So here, let's just look at the picture here. It's actually, I think, he often has quite good pictures. So here, okay, so let's just look on the left here. Here we found, let me just see. Oh yeah, okay, so we're going to talk about logistic regression later, but right now we're just going to be focusing on the linear regression. And notice, so we've got some well-behaved classes, and they're the answer given by both logistic regression, which we'll talk about, and linear regression are the same. But now notice, okay, now we're going to add some data points to the blue class. And notice that that original divider is still good enough to separate them perfectly. But because we're treating this as a regression problem, and least squares regression, these points are carrying an enormous amount of weight. So now this line is being pulled out. And now you're starting to make some mistakes because you think of this as regression. You're trying to get as close as you can to these points. Whereas logistic regression, which is going to treat things kind of more probabilistically, doesn't have that problem. So I think this is really great, just intuition for where least squares can go wrong. Okay, so the sum of squares error function penalizes predictions that are too correct. That's kind of a nice way of putting it, in that they lie a long way on the correct side of the decision boundary. And we will consider in a future section, we shall consider several alternative error functions for classification, and we shall see that they do not suffer from this. Okay, and finally it says, look, the problems with least squares can be even more severe than simply lack of robustness. And this is just essentially showing a synthetic data set from 3 classes in a 2-dimensional input space, that linear decision boundaries can give excellent separation between the classes. And logistic regression, again, does that, but least squares manages to only squeeze a tiny part. So let's just have a look at that so we know what we're talking about. So here it is. So here is our data sets. Logistic regression is able to split them, whereas least squares is, so they're perfectly linearly separable, but least squares, again, because by treating things as a regression problem, is only assigning a tiny portion of the space to being being in the green set. So another kind of big problem with least squares. Okay. So now the failure of least squares should not surprise us when we recall that it corresponds to maximum likelihood under the assumption of a Gaussian conditional distribution. So the model we're working under for least squares is that the observations, in this case the labels, should be Gaussian distributed given the input. But of course they're not, right? They're binary. So it says, by adopting more appropriate probabilistic models, we shall obtain classification techniques with much better properties than least squares. Okay, but for the moment, we're going to continue with our non-probabilistic methods for setting the parameters. Okay, so I think that was really, I think, quite a useful, I thought it was a really cool section to read. It's a very natural idea to want to use essentially regression tools to solve these problems, and I think it really highlights, like, the good thing is, yeah, we get these answers really quickly, what's essentially closed form solutions, but we can see that it's problematic because of essentially treating this problem as a regression problem, not a classification, and then least squares being very effective as outliers, and then also this additional problem that he points out with it assigning very funny, not representing the decision space properly. So I think that was kind of quite useful, and hope you guys found that useful as well. As always, just let me know if you did or you didn't. Always happy for the feedback. And I will see you next time when we talk about another approach, which is called Fisher's linear discriminant. So hope to see you then. Bye.